What is up, everybody? It's me, CJ. Today we're going to be talking about Unit 5 for AP Calculus AB, and we got the midterm coming up, so it's good to be reviewing all of this. This is a unit I struggled on, so I'm going to teach it to you so you don't struggle on it. And I got the midterm, so it's going to help me struggle on it less. So, let's get into it. The first thing you got to know about Unit 5 review is mean value theorem, which is, here, let me just explain it. So the conditions, if A and B on a closed interval is continuous and A and B is differentiable on an open interval, then you can apply the mean value theorem. And you got to remember these conditions because they may appear on the test by themselves, which is really weird, but it happened to me. So if all these conditions are met, then you can apply the mean value theorem, which means that f prime of c is equal to f of b minus f of a over b minus a, or at some point in the graph, the tangent line of a point is going to be equal to the secant line of the full interval, or the instantaneous rate of change at one point is equal to the average rate of change of the full interval. So to find c, all you got to do is set f prime of c to the average rate of change. So over here, we got an example. The function f is given by f of x equals x cubed. The application of the mean value theorem to f on the interval, the closed interval 1 to 3, guarantees a point on the interval, the open interval 1, 3, at which the slope of the tangent line to the graph of f is equal to, we just went over this, come on, you got the answer? It's alright. So at some point, the instantaneous rate of change is going to be equal to the average rate of change. So the slope of the tangent line to the graph of f is equal to the average rate of change of the interval. Should have given myself more space there. So sketch a diagram to show the mean value theorem for this function. Alright, so if you don't know what the graph of x cubed looks something like this. And I marked in our points at 1, 1, and 327 because that's the interval we are going to be talking about. And as you can see, it is continuous. It is also differentiable, no sharp points, and no discontinuities. So now we can apply the mean value theorem. If we can find what point the instantaneous rate of change is equal to the average rate of change. So let's do that. So to find c, set f prime of c to the average rate of change. Sounds good. So we got f of x is equal to x cubed. F prime of x is equal to 3x squared. Now we can set that to the average rate of change. 3x squared is equal to 27 minus 1 over 3 minus 1. 3x squared is equal to 13 divided by 3 divided by 3. X squared is equal to 13 over 3, square root. So x is equal to square root of 13 over 3, and x is equal to negative square root of 13 over 3. And this is not going to be a solution because this does not fit in our interval. Not fit in interval. So this is going to be our point where the instantaneous rate of change is equal to the average rate of change of the full slope. And if you look at it, it looks like it's just above 2. So let's just say around right here. So now we're going to sketch this out and see what it looks like. Square root of 13 over 3. So our average rate of change is going to be looking something like this. It's a little crooked, but whatever. And our instantaneous rate of change is going to be looking something like this. So as you can see, the two lines are parallel with each other, which is how it should look for the mean value theorem. And that's everything you need to know about the mean value theorem. On to the extreme value theorem. If a graph is continuous on the closed interval AB, it does not have to be differentiable, remember that. So if you're quizzed about it and you see a non-differentiable graph or function, then just know to apply the extreme value theorem, it does not have to be differentiable. Just has to be continuous. So now you can apply the extreme value theorem, which states the graph will have an absolute minimum and absolute maximum value. So now that you see that your function passes extreme value theorem, you know it has an extreme or an absolute minimum and absolute maximum values. Now you can go to the candidates test. We have two candidates right here, which is relative extrema, which is finding relative extrema. And these occur at critical numbers, and in this case endpoints as well, where f prime of x is equal to 0 or f prime of x is equal to nothing, does not exist. The steps of life for finding absolute extrema on closed intervals. So number 1, we're setting f prime of x equal to 0, or find where it does not exist, see what values of x you receive, make sure they fit into the interval, also factor if needed. Second, we find the endpoints. 3, we make a table with all the endpoints and the critical numbers. And 4, we write the sentence. Here's the sentence format. F has an absolute minimum or maximum value of number at x equals number on closed interval AB. So let's get into an example. We got y equals x squared plus 1 over x minus 4 on the interval 5, 6. We got to find the minimum and maximum values of the function on the given interval. So the first thing we got to do is we got to find the derivative. We got to find f prime of x. So we can set it to 0. So this looks like it's going to be 2x times x minus 4 minus x squared plus 1 over x minus 4 squared. Boom. So now we're going to set f prime of x equal to 0. 0 is equal, well, actually, we can distribute this out. So sometimes when you have functions, you're going to have to distribute them out, or sometimes you're going to have to factor them, and sometimes you're going to have to do both. Just like in this function, because to do that, to find when it equals 0, that's something you have to do so you can make it nice and easy for yourself. So let's just get into that. 2x squared minus 8x minus x squared minus 1. Always make sure to factor the negative to all the terms in here. So 0 is, and also forgot, over x minus 4 squared. So 0 is equal to x squared minus 8x minus 1. There we go. And this is going to be over x minus 4 squared. So one thing about when you have a function like this is when the bottom is equal to 0, it's going to equal to do not exist. And when the top is equal to 0, the whole thing's going to be equal to 0. And basically, since critical numbers occur at 0 and do not exist, that's what we're going to do. We're going to set both this top and the bottom equal to 0. So 0 is equal to x squared minus 8x minus 1. So plus 1 on each side. X squared minus 8x. We're going to have to do some completing the square here. X squared equals 1. So down here, 8 over 2 squared is equal to 16 plus 16. And usually, like, we turn it into a minus 16 because it's outside of the function. But this one is already on the other side of the equation, so it's also going to be a plus 16. So then we end up with x minus 4 squared is equal to 17. Square root both sides. X minus 4 equal to square root of 17 plus or minus that. Plus 4 plus 4 x, oh shit, oh shoot, sorry, I didn't mean to use some foul language there. So we went x minus 4 is equal to square root of 13. Take both sides, added the 4 to both sides. My mom's on a phone call outside the door. I don't know if you can hear that or not. Is anyone even watching the video? I don't even know. It's fine if no one is, because I'm watching and it's going to help me. So 4 plus or minus square root of 17, which is around 4. So x is equal to 4 plus square root of 17. X is equal to 4 minus square root of 17. Square root of 17 is just above 4, so this is going to be a negative number. This is going to be around 8. But wait, our interval is from 5 to 6. So both of these answers are not going to work. This one is too big for interval. This one's too small for the interval. And yeah, so let's cross those out. Now we're going to set the bottom to 0. X minus 4 squared equals 0. Square root both sides. Plus 4 plus 4. X equals 4. And what do you know? X plus 4, x equals 4 is also too small to be on our interval. So, too small for interval. Sometimes this happens, you know, but you can't fret because you still have the 2 endpoints in the interval, which means that one of those is going to have to be the absolute minimum or absolute maximum. And yeah, so now we got to make a table. So we got x, we got f of x. So usually in f of x, for x, you'd put all your critical numbers, but since we just have the endpoints, our critical numbers didn't fit in the interval. It's okay. We're just going to put our 2 endpoints, 5 and 6. And now we got to find f of 5. I'll do that up here. F of 5 is equal to 5 squared plus 1 over 5 minus 4, which is equal to 26. Now we gotta find f of 6. F of 6 equal to 6 squared plus 1 over 6 minus 4, which is 36, 37 over 2. 37 over 2. Make sure everything's right. It looks about right. So this is around 15, and this is around, well, that's just 26. So that means this is going to be our absolute minimum value, and this is going to be our absolute maximum. Oh, this is going to be our absolute minimum value, and this is going to be our absolute maximum value. So let's look back at the sentence format so we can write out our sentence. So we'll say f has an absolute maximum value of 26 at x equal to 5 on 5, 6. Now we gotta do the other one. F has an absolute minimum value of 37 over 2 at x equals 6 on 5, 6. Squeeze that in there. Boom. That's extreme value theorem for the, now we all know. Now we got to use first derivative to find local and relative extrema. So the steps, we got to find critical numbers, plug them into table, plug in test numbers, and then write the sentences. So find the increasing and decreasing intervals and relative extrema of y equals x squared, or x to the power of e to the power of x over x. Sounds pretty crazy. So f prime of x is going to be equal to e to the x times x minus e to the x over x squared. So now we're going to set that to 0. Should have given myself more space. E to the x, x minus e to the x over x squared. We can just take the top. we'll just use the top, set the top to 0 first. So 0 is equal to, looks like we're going to have to factor here, x, oh wait, nope, e to the x times x minus 1. E to the x does not equal 0. X minus 1 is equal to 0. Plus 1 plus 1. X is equal to 1. There's our critical number. Now we got f prime of x equal to x squared. 0 is equal to x squared. Square root of 0 is equal to x squared. So x equals 0. And x equals 1. So now we have 0 here, 1 here, 0 to 1. Plug in the intervals. 1 to infinity. Negative infinity is 0. And looks about right. So now what we're going to do is plug in the test numbers. So, in between negative infinity and 0 is negative 1. So we can plug that into our function. F of negative 1 is equal to e to the negative 1 over negative 1. Now you actually don't need to solve this. You just need to know if it's a positive or negative number. So this is going to be a positive number. This is going to be a negative number. Positive divided by negative is equal to a negative. So this is going to be a negative number. In between 0 and 1, we just say 1/2. F of 1/2 is equal to e to the 1/2 over 1/2, which is equal to a positive number. And then in between 1 and infinity, let's just say 2. So f of 2 is equal to e to the 2 over 2, which is equal to a positive number. So this means that f is going to start decreasing. It's going to come up, increase, and then stay increasing. Simple enough. So yeah. I can hear my mom talking to the college counselor in the back. It's pretty interesting. Big opportunities for college coming up. And yeah, let me make sure I did this right. So f prime is negative. I might have done this wrong, which happens sometimes. And it looks like I did because I plugged in the numbers into f instead of f prime. So I'm going to redo that. We learn from our mistakes, guys. It's okay. Alright, so we got f prime of negative 1, e to the negative 1 times negative 1 minus e to the negative 1 over negative 1 squared. So this is going to be a negative minus something, so the top's going to be negative. Bottom's going to be positive, so this is going to be equal to a negative. F prime of negative 1, so that stays f of 1/2. We got e to the 1/2 minus 1 minus e to the 1/2 over 1/2 squared. So e to the 1/2 minus 1 minus e to the 1/2 is negative. Should be negative 1. Oh wait, no, this is, there we go. So e to the 1/2 times negative 1, that's negative e to the 1/2 minus e to the 1/2, that's negative. Bottom is positive, so this is going to be negative. So this is negative. And then f of 2, so we got e to the 2 times 2 minus e to the 2 2 squared. So f of 2 equal to positive. So we're going to keep that. So sometimes it's always good to catch your mistakes. I'm sorry if you were copying down. I don't think anyone's even watching this video. So it's just going to be for me, helping me. Your mistakes make you better. No one's ever gotten better from being perfect. Remember that. And so plug in our test numbers. We got our increasing and decreasing intervals. Now we can write the sentence. So f of x is decreasing on the intervals negative infinity to 0 and 0 to 1. You can write a union if you want. It's no big deal if you don't, though, for my teacher at least. F is decreasing on the intervals negative infinity to 0 and 0 to 1 because f prime of x is negative at those points. Boom. So now we got to do their increasing interval. F of x is increasing on the interval 1 to infinity because f prime of x is positive. There we go. I think that's about all you need. And what do we need to find? Relative extrema. So there's going to be a minimum here because f prime goes from positive to negative. So f of x has a relative min at x equals 1 because f of x goes from f prime of x goes from negative to positive. I really should have given myself more space. That's on me. But yeah. And since as we can see here, it is the only extrema on the entire thing, then we basically know that it is an absolute minimum. So we can say absolute if we want. But I'm not going to. So, yeah, on to the next. So now we got to use the second derivative to find concavity and inflection points. So it's going to be the same steps, but with f double prime now. So let's read this little paragraph that I wrote of a question. Find the intervals in which f is concave up or down, the points of inflection, and the critical points to determine whether each critical point corresponds to a local minimum or maximum. So it's basically doing the whole problem that we just did over again, but added an extra layer. So here's our function. Luckily it looks pretty simple. F prime of x is equal to 3x squared minus 4x plus 1. Next up, f double prime of x is equal to 6x minus 4. Boom. So find the intervals in which f is concave up. So how we do that, we got to find possible points of inflection, PPOI. So remember that, possible points of inflection. And the possible points of inflection are going to be different from the critical numbers. So that's an important thing to remember. So set f double prime equal to 0. 0 equals 6x minus 4 plus 4 plus 4. 4 equals to 6x over 6 over 6. X is equal to 2/3. I don't know why I circled that. But sometimes you gotta circle things, you know. If you're proud of your answer, boom, X. Circle, give it a little circle, you know. I just do that sometimes. I don't even know why. It's not even something I can control. Well, I mean, it is. What am I even talking about? Let's get back to work. So that's a possible point of inflection. And now what we can do is we can put it into the table. The f double prime, we got f, we got boom, we got bang, bang, we got 2/3, so negative infinity to 2/3, and 2/3 to infinity. So now we gotta put in some test points. We can put in 0, looks pretty easy. F double prime of 0 is equal to -4. So this can be negative here. We can put in 1 over here. So F double prime of 1 is equal to 2. So positive. So that's going to be concave down. This is going to be concave up. So we find the intervals in which it's concave up or down. So I'm not going to write out the sentence this time, just for... Actually flip it. I'll just write the sentence, you know. It's not like anyone's watching this anyway. And if you are, you can skip forward. So, F is concave up on the interval negative infinity to 2/3. Let's say concave down. Because f double prime of x is negative. F is concave up on the interval 2/3 to infinity, because f double prime of x is positive. Alright. Now we got the intervals, we got the points of inflection, and the critical points, critical numbers. So this is a point of inflection. Went from a possible point of inflection to point of inflection. So right, point of inflection at x is equal to 2/3. Boom. So yeah. Now we gotta find the critical numbers and determine whether each critical number corresponds to a local minimum or maximum, which is what we just did. So f prime of x is equal to 3x squared minus 4x plus 1. So 0 is equal to 3x squared minus 4x plus 1. What do we do here? Good question. We could take out this 1. Minus 1 is equal to 3x squared minus 4x. Negative 1 is equal to x times 3x minus 4. So, can we even do that? Yeah. Man, I really do not want to get stuck right now, which kind of sucks. Are we going to have to go back to completing the square? We might have to. So, thing is, we got that 3 in the front. It's making this very difficult. So, what can we do? What can we do? Comment below what I can do, guys. Need help. Need help, guys. Let me just check over this key real quick. How's you guys' days going? Going good? Need to keep practicing myself. so I can better understand these things. Da 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 do da do da do. Trying to find it. Alright, well, it looks like I'm just going to have to factor it. Stop being a baby. Sometimes you just got to man up and just factor it out, which is annoying. We got 3x minus 1, x minus 1. That was a lot less painful than I would have thought. So, let me head back to OBS. So 3x minus 1 and x minus 1. So 0 is equal to 3x minus 1. 0 is equal to x minus 1. X equal to 1. And x equal to 1/3. So boom, those are your critical points. Time to put them in the table. F prime, we got f. So put in 1/3, put in 1, negative infinity to 1/3, 1/3 to 1, 1 to infinity. Oh man, plug in some test points. So I'm running out of space, should have given myself more space. F prime of 0 is equal to 1. So this is positive. F prime of 1/2 f prime of 1/2 is equal to, so that's minus 2, minus 2, this would be 3/4, so this would be negative. And then just by doing some mental math real quick, then we got f prime of 2, which is equal to 4, 12 minus 8 plus 1, which is equal to positive. So boom, positive, bop, negative, boom, positive. So we found the critical points, and we gotta find the maximums. F has relative max at x equals 1/3, because f prime of x changes from increasing to decreasing. F has relative min at x equals 1, because f prime changes from decreasing, or from negative to positive. And this is that's what I meant to say over here too. I'm a little tired today, as you guys can see, and wish I gave myself more space, but there we go, found everything. And that is using second derivatives and using first derivatives. On to the second derivative test. If a critical number makes f prime of x equals 0, which is the definition of a critical number, then three cases happen. F prime of x, if f double prime of x is equal to positive, then there's a relative minimum at that point. If f double prime of x is equal to negative, there's a relative maximum at that point. And if f double prime of x equals 0, then that test is inconclusive. And this is inaccurate because in real life, big recognize big and small recognize small. And that's just a little life lesson for you. So if you hang around yourself with big people, you'll become a big person. If you hang around with small people, you'll become a small person. So, example, find the relative extrema of f of x equals x cubed minus 12x squared plus 45x using second derivative test. Alright, so that means we're going to do f prime of x is equal to 3x squared minus 24x plus 45. F double prime of x is equal to 6x minus 24. So now let's find the critical numbers. 0 is equal to 3x squared minus 24x plus 45. So we can factor out 3. 3 times x squared minus 8x plus 15. Man. So 0 is equal to 3x minus 3 times x minus 5. Should give us that right there. So 0 is equal to x minus 3. 0 is equal to x minus 5. So x equals 5. X equals 3. So now we're going to plug that into f double prime. F double prime of 3 is equal to 6 times 3 minus 24. So 18 minus 24 is equal to negative 6. F double prime of 3 is equal to negative 6. F double prime of 5 is equal to 6 times 5 is 30 minus 24, which is equal to 6. So x equals 3, or we can say x equals 3 is a relative maximum on f of x because f double prime of 3 is negative and because of the second derivative test. Should probably write it a little more detailed than that, but I think that'll work. So x equals 5 is a relative minimum on f of x because f double prime of x is positive and because of the second derivative test. Man, that was a pain, but second derivative test, you understand now. Oh god, optimization. This is not it, man. I hate it. This is probably the hardest one, and I'm probably gonna have to check the key, but we're gonna give it a good shot. So, steps of optimization, and I just call this the fence problem because a lot of the time you're gonna be looking at the minimum amount of fence needed for like the perimeter of a fence that's a certain area. So steps: sketch a diagram if possible, write the equation you are trying to optimize. Equation must be in one variable. If it is not, then find another equation to eliminate that variable. Take derivative, find critical number, and apply first or second derivative tests. Verify if they are absolute minimum or maximum. Write solution in context of problem. So example, a landscape architect wishes to enclose a rectangular garden on one side by a brick wall, costing $30 per feet, and on the other 3 sides by a metal fence costing $10 per feet. If the area of the garden is 1,000 feet, find the dimensions of the garden that minimize the cost. Okay, so now we're gonna make a little diagram. So this is gonna be brick. We got our metal fences here. So this is going to be a little bit different. So this is going to be, so we'll say this is this $30. And we'll call this X. Should we call it X? No, we'll just call it X. And then we'll call these 2 sides Y, which is equal to $10. And then we got Z, which is equal to $10 per feet. I think that'll work. So now we got a diagram, write the equation you're trying to optimize. So it's the perimeter. So P is equal to X plus 2Y plus Z. Equation must be in one variable. If it is not, then find another equation to eliminate that variable. So it looks like our thing is in 3 variables right now, which is not good. So how are we going to fix this? Well, I'll show you how. So man, I really don't want to pull out the key. I'm trying to think about this. Okay, so Z times Y is equal to 1,000. And Z should be equal to X, right? What, dude? This is confusing me. Oh, dude, I really don't want to turn this off. You know, I'm gonna just pull out the key right now. Dang, man, I really wanted to get through this without pulling out the key. Frick, dude. My mom's still talking. Okay. So, yeah. So we're just going to call, okay, and this makes sense now. So the cost is, so this is going to be equal to the perimeter. And then the cost is, we're just going to call both these sides X. So this side's going to be equal to 30 feet. This side's equal to 10 feet. So it's kind of like an equation inside of equation. So we're not going to try and find the perimeter first. We're going to make an equation for the cost. So cost is equal to 10 for every X, plus 10 for every X, plus 10 for the Y, then plus 30 for the Y. So C is equal to 20X plus 40y. Now we got to get this into one variable, so we can just say if x times y is equal to 1,000, let's say, which one should we get rid of? Let's just get rid of the y. So over y, x equals 1,000 over y. So c is equal to 20x plus 40 times 1,000 over y. Or, wait, what? Okay, so I did it wrong. I accidentally got rid of the x. But it'll work either way. Now that the equation is in one variable, we gotta take the derivative, find critical numbers, and apply first or second derivative tests. So we gotta take the derivative now. So c prime is equal to, this would be equal to y to the negative 1. So 20,000 times y to the negative 1. Plus 40y. C prime is equal to negative 20,000 times y to the negative 2 plus 40. Looks good. So 0 equal to negative 20,000 y to the negative 2 plus 40 minus 40 minus 40. Negative 40 is equal to negative 20,000 y to the negative 2 divided by negative 20,000. So we get, this is going to be kind of hard, but we got to think about this. Negative 40 over 20,000. So times 5, that would be, get us to 200. Times 50 brings us to 2,000. Times 500, I believe, would bring us to 20,000. So 1/500th is equal to y to the negative 2. So y squared, if we take a reciprocal of both sides, y squared is equal to 500. Square root. Y is equal to plus or minus 500. Square root of 500. Can't have negative sides, so y is equal to square root of 500. Alright, so there we go. That's our critical number. And so now we just plug that in for x, I believe. So yeah, or we plug that in for y because we used y instead of x. So yeah, guess we do that. Well, actually, first we gotta make sure that this critical point is actually gonna be a minimum value. So what we do, we'll just use a second derivative test. So we got c prime is equal to that. C double prime would be equal to 40,000 -3. And if we plug in square root of 500, then that would give us a positive number. Which means that this would be an absolute minimum. So now we're going to plug that into our cost equation. So C is equal to 20 times 1,000 over square root of 500 plus 40 times square root of 500. Now I'm going to go get my calculator and calculate that out. See if I can find my calculator somewhere. Alright. We got 20 times 1,000 divided by square root of 500 plus 40 times square root of 500. And we get 1788.854,382 which is going to be our minimum cost. Then you got to write a sentence. So we'll just say is our minimum cost, and we know this because it is the only critical number and gives a positive value by the second derivative test. It is an absolute minimum, also because it only has 1 point. It is the only critical number. And that's about it for Unit 5. Hope you guys do good on the test. This video was kind of long, I think, so it's alright. It's a little late. I better get to studying something else. Hope you guys enjoyed the video. Bye. Have a good one. Good life. Good test.